are very happy to have Vincent from UC Berkeley, and he will tell us about the TWAS quantum gravity in the lab on quantum processes. Please.
All right. Hi, everyone. Thanks to the organizers for giving me the chance to speak. When I found out that Sepper was giving his talk on quantum gravity in the lab, I was pretty relieved that half of my talk would be covered for me. So, Sepper kind of mentioned these two regimes, the first being kind of this infinite temperature scrambling regime, and the second one being the more interesting gravitational regime. But given that today we're going to be connecting with real quantum devices, we have to start somewhere. So this is mostly going to be on that kind of first part of primarily scrambling-based physics. And this is joint work with Bert, Ilya, and Miro from Lawrence Berkeley Lab, and also with Brian Swingle, who's at Randace. OK, so the motivation for this, I think it's pretty safe to say that many of us here are interested in how quantum gravity actually works. One day it would be nice to have experiments that kind of help either confirm what our current leading theories are, or even, perhaps more excitingly, disprove them. When it comes to actually doing these types of measurements in the lab, it's also kind of exceedingly difficult. If any of you are planning to make a black hole in your lab, please let me know when you do that so I can try to stay outside of the horizon. So along this vein, though, there's been a recent idea to maybe leverage this ADS-CFT duality to indirectly probe quantum gravity, assuming we have access to better and better quantum computers. And again, I'll stress that today I can't really be claimed to be doing any gravitational physics. OK, but one thing that I do want to highlight about this line of work is that in our search for quantum gravity, a lot of it is asking what principles of quantum mechanics will extend in a higher theory of quantum gravity. But what I find so fascinating about this is that this connection really goes both ways. By even thinking about gravitational physics, we're already learning something new about quantum mechanics, which is something we thought we already knew. OK, so today I'm going to tell you about some recent work that's being done on literally taking this wormhole teleportation protocol and putting it on a quantum device. This is obviously, well, there are some nice connections with previous experimental work where they basically have demonstrated verified quantum information scrambling. So as Sepper alluded to, the success of this traversable wormhole protocol working, at least in the infinite temperature regime, is very much a sign of scrambling physics. OK, cool. So to give you a roadmap of where we're going, I'm just going to do a quick review of what it takes to succeed in this traversable wormhole protocol. This is partially overlapping with what Sepper has already discussed. The other thing that I wanted to do was just briefly discuss operator size and what this two-sided coupling does exactly. I think this was already touched upon in previous talks throughout the day, but because everything here is now just a handful of qubits, it's easier to make this a little bit more explicit and get a sense of what is actually happening. And then finally, I'll tell you about the actual experiment that we did and the model we considered and so on, and then I'll show the results of our experiment. OK, so the starting point, which Sepper already did a great job of reviewing, is the so-called traversable wormhole protocol. And I guess I just wanted to share this picture of, well, OK, so on the right is the picture we normally see where the two CFTs left and right are on opposite sides. And the Penrose diagram you should think of as being kind of the dual picture to what is going on in those CFTs. But the reason that we find this so fascinating, right, is if you imagine you have two black holes, each with their own horizons, right? The horizon is where information cannot escape from. It's kind of amazing that you can send something in on one end, it goes behind the horizon, and it comes out of the horizon of another black hole. So I don't know, that is just kind of an amazing fact. And the emphasis today, again, has been what is in addition to that being surprising, the fact that this same circuit, if you take these steps of preparing the thermal field double, time evolution, and inserting an operator, the fact that you can do that in generic chaotic quantum systems is, from my perspective, nothing short of magical. Okay. So again, what we're doing here today is taking this wormhole-inspired teleportation protocol and putting it on a quantum computer. So up here, I have kind of the circuit diagram for what's going on. I guess this one I've drawn with time going to the right rather than up, but it's the same circuit as in Sepper's talk. And the key ingredients we'll need are bell pairs, so the TFD at infinite temperature, backwards and forwards time evolution, and then the ability to apply this two-sided coupling, where again we're just taking the left-right operator, the product of left-right operators. Okay. Now, this protocol was analyzed not only in the Quantum Gravity in the Lab paper, but also in a very nice paper by Tommy and Bryce and friends here, as well as collaborators on the East Coast. And they were really interested by this protocol and wanted, again, a more microscopic description. I'll say a little bit more about that later. But it turns out that if you want to ask whether or not this protocol succeeds at teleporting quantum information, you can basically characterize whether or not that will happen by studying the following correlators. You take the operator on the left at minus t and the operator on the right at positive t. And this is basically like calculating the fidelity of, if you inserted a line here, it would be kind of like the fidelity of an operator on the right with the operator on the left acted on by the coupling. Okay, so if you calculate these things, what they predict is that if you have that R is maximal, which in the case of bell pairs, this is kind of trivially satisfied because you have the right entanglement structure. But the second condition is a little bit more interesting. Okay, it says that the phases that you get have to be aligned. In this case, we're only teleporting a single qubit. So we need to calculate this correlation function for all operators acting on a single qubit. So we have these four operators here. Okay, I guess I'll pause for questions in case there are any. Okay. All right, so I think I can go through this part a little bit faster given previous talks discussing operator size and growth. The basic idea is, at least for qubits, the polystrings form a complete basis. You can then ask, given this distribution over polys, what is the support on polystrings of fixed length? Generically, if you have a chaotic theory, you can ask, what happens to this distribution over time. I'm going to basically show, this thing, which is maybe a discretized version of some of the previous plots of operator growth. Suppose you had some initially local operator z. Under time evolution, it might evolve into some superposition of polystrings. And eventually, if you have like a chaotic system, you'd expect that a lot of the support is on these higher weight strings. Okay. Now, the next thing I want to discuss is what does this two-sided coupling actually do in the experiment? I think this point was stressed also in Bryce's talk from last year. But one way you can think about this coupling of e to the, my slide didn't update. Okay, yeah, so remember that the coupling is basically products of ZZ operators on the left and the right. Hold on, let me just double check that. Oh, okay, here it is. Yeah, sorry, this is the real slide. Okay, so as a reminder, our two-sided coupling is the exponential of this product of Z operators. Okay, and it turns out that polystrings are also the right basis to understand what this coupling does, at least in the infinite temperature limit. And so if you start with Bell pairs, okay, and you act by some polystring, it turns out that the state you get here is an eigenstate of this coupling, where the eigenvalue is given by the size of that Pauli operator. Now here I've got a little z subscript because technically the way this eigenvalue shakes down is that this thing will commute with any z's in the Pauli string. So technically you're only measuring the size of non-z, non-identity operators. And so this is kind of like if you had a string that normally looks like a size 3 string, you have to subtract 1 because this technically commutes with the coupling. Okay, so the bottom line here is that if your operator, which is again a sum of polystrings, if your operator, which is a sum of polystrings, if the size distribution of that operator is tightly peaked about some size, right, so they all have size 3, then this state is also an eigenstate of the coupling, in which case this two-sided coupling just applies a global phase. Yeah. Okay. So putting this together, given some chaotic Hamiltonian, you expect that your time-evolved operators have a peak size at the extensive value. And so if you wait until then to apply your coupling, you're just going to get a global phase. And then the condition outlined above, well, if all of your operators have this same size distribution, then the phases that you get will be aligned. Yeah. Good. Yeah.
I think usually the size will concentrate compared to, say, total size is n, and the distribution width will be small compared to n. But it's still big compared to 1. It should probably peak, the width is probably around square root of n. But is that, from the coupling, it means this.
Right, it's not an exact eigenstate. Yeah.
So it seems like the approximation that this is applying a global phase is only true for a very short time.
Right. Yeah, so yeah, what is the argument that it remains for?
So the coupling has a coefficient that's like 1 over n. It's like the coupling g over n times the sum of n. Yeah, so it's like size over n.
Oh, okay.
Yeah, good. Sorry, I forgot to include that normalization. Thanks. Okay, so far I've kind of outlined these abstract conditions again for like when this succeeds. Now we're going to dive into kind of the experimental setup. So we can actually study how operators grow under a particular concrete quantum model, which is the so-called self-dual kicked quantum Ising model. I'll say a little bit about kind of the device considerations we had in mind. A lot of this, I'm going to skip over the details, but it's to kind of show that a lot of non-trivial work went into this. But I'll say a little bit about our plans to release a software package that basically takes care of a lot of this hard work for you. And then I'll show some of the numerics for carrying out this experiment, and then finally I'll present what we got from the actual quantum device. Okay, so this model we chose to study was introduced by Bertini, Koss, and Prosen. And one nice feature about it is that time steps are discretized, so it's kind of like an alternating model where in one step you have ZZ interactions with some on-site Z's. Here, this is a constant for all pairwise interactions, but these on-site fields are randomly drawn. And then the next step is basically transverse fields with strength B. So this might remind you of like QAOA, or I guess if you study flow K models, this is also pretty common. But the reason that this model is interesting is that you can show that for a certain parameter regime, that entanglement entropy grows as fast as possible. So in that sense, it's kind of like the minimal thing you could write down that exhibits chaotic behavior. And let me just point out that this thing is also pretty ideal for quantum simulation. If you look at these terms, like everything in UI commutes with self, so you don't really have to worry about Trotter errors. And because these are separate time steps, you can just do this after. Yeah, and then the other thing is that if you're interested in negative time evolution, which is a key ingredient for us, you basically get that by either changing these angles to be negative or over-tuning your angles so that you get effectively the same effect. Okay, so the devices we had access to, or I guess the devices that my collaborators at the lab had access to, include the IBM Q machines, and I think the most recent Honeywell device, the H1. Obviously, it would be very interesting to push this to as large a size as we possibly could. I'll just say a little bit about the trade-off there. Generally, you need to run this for a time that is of order the system size. And so the number of gates you need, well, the size of your Hamiltonian grows with n, and then the depth is like roughly n as well. And so the number of gates you need is order n squared. So given this constraint, our full system size was 7, where 3 of the qubits, you have 3 qubits on the left and the right, and then 1 message qubit that gets injected in. Okay, and then the other thing, of course, we need to consider is that these gates will be noisy. And so to get try to maximize the signal that we get, I'm going to choose to fix these kind of random on-site terms, which were h's, to be 0. Well, okay, what we found in the numerics was that the biggest signal you get is actually for h equals 0. And then if you also use the fact that we're at the critical point of this model, you can show that the dynamics are actually Clifford. Okay, so down below, I've included some of the layouts that are available on IBM's cloud service. This layout over here is almost begging to be made into a thermofield double state, where like you call this the left system, and you call this the right system, and you can just prepare entanglement across those. Whereas over here, it looks like you have more qubits, but if you wanted to pair them up into left and right, it looks like it would be a little bit more work. It turns out that even though this had a better connectivity, the gate errors were much lower on this, and so this one was actually the one that got better results. Yeah.
Sorry, you say you're setting all of the d fields to 0 in the chain?
Yeah.
So if you go, can I see the model again? Sorry.
Yeah. Uh-huh.
Isn't it then integrable?
Yeah.
That means it's not chaotic.
Right. Good. So this specific thing, good. So this experiment that we did is not chaotic, but like I guess we started with this model which has some nice properties, and then we found that if we're trying to extract a signal from the device, like the particular limit that worked best was non-zero h's. It turns out that you get actually a pretty similar signal if you just take h, small but non-zero. I'm not sure what that says about the integrability, but
H is small and non-zero, then it's not integrable anymore.
okay, so
Also, when they have this model is nice when they take H to have some huge variance. It's like all the signals clean up in the limit where the variance becomes huge.
I see.
Like when the variance is small, actually the signals you get from this model are super noisy.
Interesting. Oh, interesting. Okay, I wasn't aware about the variance condition on the h's,
Yeah,
but
so
that's.
the point is that when you make the variance very large, then
Oh, they don't rotate by the same amount, I guess.
rotate by the same amount. You wash out loads of interference. The problem is when you're dealing with an integrable model, you get lots of interference effects coming in. But when you take H to be have a huge variance, you wash out lots of this interference and get this model is famous from that paper because it has this really clean spectral form factor, and that clean spectral form factor comes out in the limit where H has a large variance.
I see. Okay.
But H equals 0 is like a completely different model.
Yeah.
But this is not one-dimensional, right? It's connectivity that is not one-dimensional connectivity.
I thought this is
No, it is. It is one-dimensional.
No, but if you go to the next slide, so are you going to apply that signal
Right, right. So you can think about it like it's a one-dimensional logical lattice, but then when you want to compile that down, there's kind of like routing overhead. So yeah, like we're basically embedding something that has the structure of like this onto this, but effectively the dynamics are still in 1D.
Your goal is to implement
Yes, 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 yeah. Yeah.
I'm trying to follow you guys' discussion. It's very fast for my level of processing. I mean, this thing that it makes the dynamics Clifford was so surprising here, right? That's not what you would have expected to make this work, right?
Yeah, yeah. There are kind of a couple of nuances in the way this ended up working. So the first thing that we did was basically we picked random h's, and we were like, okay, of all the h's you can sample from, which one gives the largest like teleportation signal? And it turned out to be this for this system size for 3 time steps. I can say a little bit more later, but the idea, like the thing that you've correctly pointed out, is that because these are basically periodic, a couple of things happen. One is that there's no sense of like a scrambling time, and then the second is that we actually don't get perfect phase alignment for all of the operators, which was, I forgot to point that out, but the conditions that were outlined before are not fully met, but partially met. So we're not able to teleport a full qubit's worth of information, but rather a classical bit of information in a qubit. Basically, there's dephasing noise. So we end up transmitting basically the Z component of the qubit's information. Yeah.
I think you only need operator growth for this thing to work, right? You basically need operator. I mean, you don't need chaos in the sense of real chaos. I mean,
That's true. Yeah.
Cliffords are never chaotic in the sense of say eigenvalues are boring. All basis space is very small, so it's not really chaotic in any real sense.
Right.
It's
Right.
always interpretable.
Yeah.
Because I think in Clifford circuits, single site operators can still grow into many body operators, right? Sorry? In Clifford circuits, a single site operator will still grow into a many body operator.
Mm-hmm.
But I think that model, when you write it in terms of fermions, is just quadratic in fermions. So single site operators stay single site operators.
Right. In the spin picture, it still grows, even though it's
But with a strain in between.
Yeah.
Oh, is that what it is? Oh, I see. So
Wait,
the
sorry, could you
fermions are still like quadratic and local and everything.
Yeah.
That's right. Oh, okay.
But free fermion can also grow, right? You wouldn't call it chaos.
Right. Chaos is not necessary for this. Chaos isn't necessary for this experiment to work, but I guess you can take it as part of the motivation for studying, the BKP model on this.
This is an integrable model, and yet, because you can map it to free fermions, and yet in this operator basis, you still see operator growth.
And it's worth pointing out that
For operator strings in this basis.
Yeah. Oh, but not just operator strings, actually Jordan ligand strings.
Oh, okay, yeah, that's right.
Yeah. Like it's. But I mean, it is kind of funny because you can, under a pretty straightforward transform, you can make it look like the operators aren't growing at all.
Right. Right, exactly.
Right. So actually,
So it's very basis dependent.
Yeah, somehow.
good. So
You're measuring in the Clifford basis.
Yeah.
That's why you're almost, that's the basis relative to the first of the magnitude.
That's right. Yeah, that's right. That's right. Uh-huh.
Even though the dynamic is trivial on a different basis.
Right.
yeah.
Yeah, you're saying you only need to pick one basis where this thing works in, and if it works in that basis, if you can find a phase that lines up for a bunch of different operators, then
Yeah, and it's worth pointing out, because it's Clifford, I mean, the size distribution is
Peaked.
it's
still
discrete
the
and
function, and
yeah.
it's just that specific size. So it's you don't have to worry about these phase fluctuations that
Right.
came up before. So in this case, it really is just an eigenstate that
Okay.
operates.
Okay.
Is that what you meant by teleporting a classical bit? You have to be in a particular basis?
No, that's a separate basis issue. Yeah.
Okay.
Yeah. So I guess in this condition, it's not necessarily true that that all operators have to be the same size. It just has to be that the overall effect with G times the coupling gives you the same phase. I don't know if that clarifies it for anybody else, but the fact that it's like not completely scrambling is okay for our purposes of getting the phases to align. Okay. Good. Okay, so good. So this is what you would get if you run some numerics where you insert psi in the plus eigenstate of the z operator, and you run 3 time steps of time evolution. And the way you should see this, so technically there's a y decoding operation, so these values are negative. But you can think about perfect fidelity of teleporting. This state occurs when the z expectation value of the output qubit is maximal. Okay, and that occurs at a particular value of the coupling. We can actually understand why this happens because of well, sorry. Before I say a little bit about why that is, I just want to take a second to compare with the Haar random calculation that was done in the quantum gravity in the lab paper. So what they showed is that if you take your time evolution to be Haar random, and you think about this circuit as a quantum channel, that channel has the effect of depolarizing noise followed by a bit flip. Okay, so it's basically perfect teleportation, but you just kind of shrink your magnitude away from the Bloch sphere. We ended up doing some channel tomography on this particular circuit, and we found that, but there's also a dephasing noise. Okay, so basically any x or y component of your qubit gets squished. And the reason this happens is actually because the phases of z and I are aligned, while the phases of x and y are not aligned for any choice of g. And the reason this is significant is because you can write the density matrix of, say, this state as a sum of I and z operators. Okay, so to take a step back, what this curve is plotting is basically probing, how much the phase alignment of the operators z and I are. At the end of the day, the experiment we're doing is we're injecting this 0 state in, and then we're measuring the z expectation value of the output qubit. Okay, and this is kind of the shape of the curve that you can just calculate via numerics. Okay, cool. So yeah, I advertised a little bit at the start that we'll be releasing, hopefully soon, some kind of software to go along with this so that people can run this experiment on their own, basically. To give you a sense of what kind of happened under the hood, I showed some example layout selections earlier, and those are non-trivial things that feel like they're getting in the way, but very important to deal with if you actually want to run this on a quantum device. The second thing I want to talk about is that not all gates are created equal. Sometimes some gates are noisier than others. And so part of this package will also handle the compilation for you. So I have a table here of some different ways of taking our logical circuit, which is just this time evolution, but then you actually have to go and put that on a quantum computer. So something you can do is ask, like, if you assume that control knots are your most expensive thing, maybe you want to minimize that. This package will basically handle that type of conversion for you. And then, of course, error mitigation is a big deal when you deal with physical devices, but maybe I'll skip over that a little bit for now. Okay, cool. So here's some experimental results that we got. On the left is using the IBM machines of the layout that I showed earlier. The signal noise was, the signal was pretty noisy on this. Straight out of the device, we get like a 20% signal. if we include all of the error mitigation techniques, we can kind of see a signal of roughly 35%. On Honeywell's recently released machine, I want to say, oh, actually, okay, October 2020 was not that long ago, but anyways, their gate fidelities are actually really high, so we already observe like an 80% signal without the need for error mitigation. So I thought that was pretty cool. Again, this is injecting a 0 state and then asking about the z expectation value of that output qubit.
How many qubits are you using?
Yeah, good. So this is like 3 sets of bell pairs plus 1 for the state injection, so 7 total. Yeah.
The reason that you basically have perfect fidelity is because you're assuming 3-4? Because, I mean, large, small n, you don't expect to get the perfect signal normally, right?
Yeah. Well, I think part of it is also the infinite temperature limit also simplifies a lot of this. Yeah. Yeah. I think that's more. Well, that and Clifford's make the size distribution, peaked for all time. So those two things combined. Yeah. Yeah.
Have you tried rotating the initial qubit and seeing if you can follow the, so here you're preparing it down and measuring the resulting, but can you go everywhere on the block sphere? Or?
No, yeah. So you're saying like let's prepare a plus state instead of yeah. So it turns out that if you run this okay, so here I kind of picked 3 time steps because that was like roughly the depth that we could push. If you stick with 3 time steps, then your plus state, okay, so maybe I should have included this table. But basically you can track the length of the strings for initial x, y, and z like perturbations. For 3 time steps, good. Good. So I said that we can understand our teleportation of like the z basis based on the fact that theta I and theta z are aligned. So that happens at 3 time steps. And at 3 time steps, the phase of x is kind of just, you can't do it. But if you waited like a step earlier, then it turns out that the identity and x would be aligned. And so you could transmit a plus state then, but then you wouldn't be able to transmit the z at that time.
So it sounds like you're able to transmit a classical thing.
Effectively, yes. Right. Okay, cool. Any other questions? All right, cool. So that actually, yeah, this was kind of the last major slide I had. Yeah, so just to kind of summarize, what we demonstrated was this wormhole-inspired teleportation protocol. I'm happy to talk about some of the differences between previous scrambling experiments, but I think this is pretty cool to have seen actually done. One thing I want to emphasize is that we did this without access to the physical device, right? And that's kind of a feature, not a bug. It means we weren't able to tune specifically like our hardware for the experiment we were doing. It's kind of cool that you can do this all via the cloud. And what it also means, right, is that other people can also do this and try things out. As I advertised a little bit earlier, we're planning to release the software that contains a lot of this error mitigation and compilation tools. A large part of that was done by Ilya Shapoval at the lab, so he put in a lot of really good work on making that streamlined. Some obvious next steps would be to run this on finite temperature thermofield double states with larger number of qubits. And I think related to Sepper's talk, like longer term, I think this is kind of a cool way to discover more holographic theories. Right now we don't have that many candidates as far as I'm aware. And so it might not tell you much about the gravity picture yet, but it seems like a nice sanity check for anything that you want to test. And likewise, I could actually see this being a benchmark for quantum devices, people building quantum computers, this being a standard thing you could try to calibrate against. Okay. So I also want to do a quick acknowledgments for, in addition to GeoFlow supporting this project, a lot of this was supported by programs at the lab, including ARQC, the quantum algorithms team, and also we were able to get access to Honeywell thanks to people at Oak Ridge Lab. So with that, thanks.